Read the book. I'm supposed to be a math teacher. I'm talking about the movie. This is college. You guys need to go read the book. I'm going to calculate the line integral of some vector valued functions. If you're ever just asked to calculate a line integral, they always mean flow or work, which is also the tangential form. The definition is to project the vector field onto the unit tangent vector to the path, but that doesn't really help you calculate the answer to a problem, so you're going to use the differential form if you're ever trying to work out an actual example. I'm going to calculate the line integral of this vector valued function. So this represents the amount of work that this force field does to move a particle from this point to this point, a straight line path. The first step in any line integral problem is to parameterize the path. I'm using final minus initial times t plus initial, but this is really easy because the initial point is just 0, 0, 0. In the theory, we've been calling this parameterization R of t. The standard choice for letters is to call the x component of the force m, the y component of the force n, and the z component of the force p. The final line integral that I'm going to set up here needs to have everything in terms of t. So I need to transform all the components of my vector valued function into a function of t. M is equal to 2y, and from my parameterization, y is equal to t. So I'm just taking the points on the curve and plugging them into the vector valued function. I didn't even do this on purpose. Look, 42. So now I've got all the m's and the n's and the p's all in terms of t, but in order for me to use the differential form, I need to figure out what dx, dy, and dz are. But that's easy because I can just take the derivatives of my parameterization, and that will give me a differential relationship between dz and dt. Yeah, I forgot my t squared. T times t is t squared. You guys in Calc 3? The differential form really makes this so easy. M dx n dy p dz. F dot t represents the actual force that the vector field does on the particle, and ds represents a distance. The units of force are newtons, and the units of distance are meters. So the units of this answer should be Newton meters. Those are the units of work. I'm going to repeat this exercise, but I'm going to move the particle on a slightly different path. In the first example, we calculated the work done to move the particle along the red path. And now I'm going to change the path a little bit. I've just added a slight little curve to it by making this t squared. So we should end up with a different answer. When you drive somewhere in your car exerts a force in order to cause the vehicle to move. And if you take a different path, then it's going to be a different amount of work for the car to deliver you to your destination. So we should get a different answer when we do this calculation. Let's find out. What's happening differently this time is the dy term. Since y is t squared, when you calculate the differential dy, you're going to get 2t dt, which was different than last time. You guys haven't seen this movie? It's adorable. It's adorable. This guy was so popular too when they came out with it, like probably a million years ago. Nobody knows what I'm talking about. I got about 57.3. So it was more work to move the particle along the curved path than it was to move it along the straight line path. In my opinion, these line integrals with respect to just x or y or z is actually more simple. I calculated the differential dy based on what they gave me for y. I'm just realizing how bad mathematicians are with parentheses in these integrals. I guess it's implied that when you put a differential at the end of an integral, it applies to everything inside the integrand. So there should really be parentheses right here. This is x and this is y, so I just substituted them in for x and y. And I got 98 thirds. I got a layer for most def. I got a most def layer. Maxwell approves. James likes it. He gives it the thumbs up. They're really like this, but I'm going to scale them down because I don't want it to make my graph too busy. These vectors that I've drawn all have 0 horizontal component, and then the vertical component gets bigger the farther out that we go on the x-axis. And here's a path that I've chosen, just kind of makes a neat little parabola, and we're going to move in the direction of increasing t. When you plug time 0 in, you get the x coordinate is 0 and the y coordinate is 1, and then as time moves on, the particle will move along the parabola, and then at time 1 the particle will be at 0, 0, as moving in this direction as t increases. Now I'm calculating the differentials from the parametric equation. This is the x coordinates and this is the y coordinates of the points on the path. So these represent how the x and y coordinates are changing for a very small change in time. And then these are the components of the vector for each point on the path. Work corresponds to the tangential component. And then we use the differential form to actually calculate the answer. Then I distributed the negative. And I got negative 2/3 Newton meters of work. The math here is answering the question, how much work did this force field do to move the particle along this path? All of these forces are pointing away from the direction that the particle is moving. In fact, the unit tangent vector at the vertex of this parabola is exactly in the opposite direction as the force. So this means that the force is not helping you move the particle along the path. What this calculation reveals is that you would have to do 2/3 Newton meters of work in order to move the particle along the path.